Okay, so thank you for coming to the talk today. Welcome. We're going to be talking about what lies beneath. That's the title of the talk, and the idea of it is that we're going to look at below the surface of what happens when a Java program executes. Normally, Java developers just look at the code and they just think, well, magically something happens. You know what public static void main is going to do, and your expectation is it will just do it. But a lot goes on behind the scenes, and that's what we're doing today. I'm Maurice Naftalin, and this is my introductory slide, which I'm just going to jump over because it says how wonderful I am.
And he is, actually. Believe everything he says. I'm Dmitry. My biggest achievement is being a chief disorganizer for JCREAT and JAlba on conferences. By the way, we have a few free spots for the JAlba, so if you're interested, come into Edinburgh, joining us for the event, come talk to us after the talk.
And conferences are a great thing. They're like conferences, only not organized. And you have a lot of fun at them.
All right, so let's see what lies beneath. Is that going to be another Hello World?
Yeah, well, more or less. So we're going to take a really simple program. We've written a tiny program. It's like 10 lines, something like that. And we're going to find that actually we're going to be able to talk for all of 45 minutes about what's happening in that program. We're going to see what happens when we type it. And it turns out it's amazingly complicated and interesting. I'm just going to turn this on so that it goes to so that we get the what's it?
Just stay with us for a second.
Right, that's better. I like to be able to see what's going on.
You see that on the screen.
Oh. Okay.
Forget about it.
Should we check that out? Why is it doing that? Oh, it's my fault. I must be mirroring. Shit. Sorry. Oh, right. Okay. Right.
Well, as any presentation goes, first we have to find the computer.
It'll work now. Jesus. I'm so sorry. Oh, no, that's not what I want. Jesus, come on, Maurice.
Hey, now we see it again. All right. So what's inside our magic application?
Everybody knows that how Java works. It's not a secret. You run Java-C on the source code. You get bytecode for it, which is often talked about as being the machine code for a virtual machine, and then it's interpreted and run on native code. We're calling this a template interpreter. I think that's the proper name for it. The idea of the template interpreter is that it takes each bytecode instruction and it translates it to a fixed set of native instructions. We're going to be looking at x86 code in this talk. And if that seems quite a complicated way of doing things, we're going to find out during this talk that actually it gives the possibility of a much improved performance in the end, much improved performance over static compilation. So let's have a look at the little program that we're going to be running, our Hello World.
So our monsters application consists of an add method, which adds a constant 254 to a value. Then we have the meat of the application. This is compute, where we divide the value passed as a parameter by a constant deadbeef and call an add method. And the main method, which will just use CacheBabe to compute. Hands up if you know what the CacheBabe reference is all about. Okay, we have one person in the room knows what it is. Okay, two people know. Well, CacheBabe is a magic constant that is in every compiled class file since Java 1.0. And do you know how this
the story of this sexist meme is that the guys who were developing, or actually it was just James, I think, James Gosling, who was developing this. They hung out at some they were hung out at some cafe, and he's supposed to have fancied the baristas, the cute baristas who worked there, and that's how the Cafe Babe got into those sexist bytes, got into every single Java class that will ever be written. But we're stuck with it. So the way this program will work, I just want to drive this home because we're going to be looking at the bytecode execution of it. Is that we're going to call the compute with this value cafe babe, and that's going to then call the add method, having divided cafe babe by dead beef. That gives the value. That gives the answer 1. That's the result of that division. That 1 is then going to be added to 254 to give the result, which is XFF, 255. So we'll have a look now at how the bytecode executes when that happens.
All right, so we have this. Let's have a look at the bytecode. So if you run Java C on our program, we get a bytecode. JDK provides a tool that allows you, it's essentially a disassembler for Java. It's called Java P. If you run Java P on your program without any flags, you're going to see essentially your Java code. It's synthetic, it looks like the same code that you wrote. But if you use Java P with minus verbose flag, you're going to see all this. And we're going to explain in a second what it all means.
So this is a highly edited version of what you would get if you ran our little program through Java P. It's 3 sections that we've highlighted here. There's a constant pool, which is, as the name suggests, it's where constants are stored, like literals that occur in the program, and method references in this case, and various other things as well. Constants that will remain the same throughout the execution of the program. Then for every method, there are 2 parts. There's the actual code itself, the bytecodes, which are under the heading code there, and there's also a local variable table, which when a method is first called, contains by convention in slot 0, the first line there, it contains for an instance method, it contains a reference to the instance of the method is running in.
At this point.
At this pointer, in other words, like it says. The subsequent lines, subsequent slots, contain the arguments with which the method was called. In this case, the method was called with a single argument, which was cafe babe, and that is what's going to be in slot 1. But what we've got there, it doesn't say cafe babe in slot 1 there, and the reason it doesn't is because this is the output from Java P, minus verbose.
All right, so let's walk through how this whole thing is going to be executed. So VM is a stack-based machine. Unlike our computers that are register-based, they store stuff in registers, VM uses an operand stack to run the code. So how it all works, it basically walks the bytecodes from top to bottom and use an operand stack to execute the operations. So when we start execution, we have an empty operand stack without nothing on it. And the first thing we do in the method, we do aload _0, which aload is loading a reference from local variables table at slot 0. As Maurice said before, at slot 0 we have this pointer. So what aload does, it loads the slot 0 from local variables and pushes it on top of the stack. So the result of the operation, we have this on top of the stack. So then we go to the next instruction, which is iload _1, which is loading an integer value from a local variables table and pushing it on top of the stack. So the same story goes. We push now the value that was passed to the compute method, and in this particular case, we show an execution from our main method. So this is the cafe babe constant. It's pushed on top of the stack and pushes this down. So the top slot is now cafe babe. Then we have an LDC, a load constant bytecode, which loads a constant, but this time from the constant pool. So you see -2 there is a reference to the constant pool definition up there, and this is our dead beef constant that compute method divides by. And that is then at the end pushed on top of the stack. So stack looks like dead beef followed by cafe babe followed by this. Then finally we are ready to execute the division. Maurice, do you want to talk about that?
Sure. Well, the division is it's really straightforward, isn't it? I mean, dividing integer division of 2 numbers. The result of the division is the operands to the division are going to be consumed, so they'll be popped off the stack and they'll be replaced by the result of the division. In this case, the result of the division is 1, so those 2 disappear. We have 1 now on top of the stack. Almost finally, we call the add method. That's the invoke special bytecode, and that uses the top value on the stack as its operand. So we go off and we call the add method. We add 1 to as we know, it computes 1 plus 254, and it returns the value. The return value from that will replace the operand, the stack elements that were used as arguments to the method. So 1 will disappear, it's been consumed, and it will be replaced by 255, the return value from add. Finally, we return from the compute method, and the value that is returned from a method is, again, by convention, it's the top value on the operand stack. In this case, 255. So, I mean, that's all very well, but like what we've talked about here is only the bytecodes themselves. We haven't actually said anything about how they're going to work when they're interpreted into machine code. And you might think this is pretty straightforward, because after all, integer division usually has a corresponding machine code instruction. So why don't we take a look at what actually happens, what the native code that is generated corresponding to that IDIV instruction in the bytecode. Well, let's see what that looks like.
Well, first of all, it depends on how you run, with interpreter or without. But in particular case, when you run in the interpreter, by the way, you can use the flag -XX plus PrintInterpreter to get the assembly. It looks as scary as this. So if what you see on the slide, you see a single div instruction that is supposed to be, well, a single CPU instruction, and if you like squint a bit in the middle of the screen, you will find IDIV %ECX there. But what on earth everything else is around it? Let's try to figure it out.
So the first block of code there is no problem. The first block of code is basically taking what's on RSP there is the stack pointer. And it's moving RSP, it's taking the top 2 elements off the stack, and it's putting them onto the, it's putting them into registers, because the x86 is, of course, a register architecture. So we have to get the values where the x86 machine can cope with it, can handle them, and that means putting them into registers. So all that's happening in that top block of code is simply extracting them off the stack and putting them into registers where they can be worked on. The next block of code is this one. It's the thing that actually does the division. The last four instructions there are just instructions to the template interpreter. So you can see there's a div instruction in there, an IDIV instruction in there. And we were looking at this last night and saying, why on earth is it so much work to make just simply to do the thing that to translate a division into a division? And it took us a while to figure it out. So let's see, maybe you can figure it out more quickly than we could. It's dealing with a special case for integer division in Java. Can you think what that special case might be? Okay, give them a hint.
All right, what about mass.abs operation? Have you ever been bitten by not being able to get an absolute value of the integer? Which one integer in Java doesn't have an absolute value? As a gentleman there suggests, it's integer mean value. Because integer mean value by magnitude is 1 bigger than the integer max value. So there is no complement positive number on it. Which means we have to deal with integer mean value case in one very peculiar case. So we figure out what this 0x8 million there is basically integer mean value.
So what combination of operands involving integer min value would mean that you couldn't just do an ordinary division in Java? So it's going to be something that wants to produce a positive value that you can't represent. It's unrepresentable. If you divide integer min value by something, it's going to give you 1 greater than integer max value. What's the something? It's -1. It's -1. So if you divide integer min value by -1, you're going to get 1 greater than the largest number that can be represented in Java. And that's what all this code is about. It's detecting that special case.
Or presented in a different way, we can look at the flowchart what actually happens. So what you see in the code block there is that first check if the dividend, in our case it's cafe bake, is equal to mean value. If it's not, we jump somewhere else. But if it is, we do some housekeeping. I'll explain later in a sec. And then we check afterwards if it's a mean value, if the divisor is -1, because dividing mean integer by -1 gonna produce something that's bigger that doesn't exist. So in this case, it's a special case dividing mean value by -1, and we have to skip the division. So what the program does in this case, it jumps over the divide instruction and exits. So it doesn't do actual divide because the divisor mean value is the actual answer. So it can skip the divide. If it's not -1, or if the dividend was not mean value, we have to do the actual divide. And we prepare the arguments with sign extending the value to 64 bits. We call the diff, and the result of the diff is put in 2 registers. So EAX will be a quotient of the quotient, the result of the division, and EDX will contain the remainder.
Cool.
And the EDX0 and the mean value was that because we never will have remainder in that case.
You have a question? Sorry, why? Yeah. When he gets loaded with the value, well, this point it doesn't matter. So EDX has been zeroed by the XOR operation.
Ah, yes, okay. That's a fancy way to set a 0 into itself. And the answer is complicated, but one of them it takes less bytes to encode it in machine code, XORing register with itself. So, and the CPUs can optimize it for us. It's really thick, but it's basically it's a fancy way to set a 0 into the EDX.
Okay, so that gives you a little picture of what understanding one single bytecode instruction is about. Let's take a step back for a moment and take a look at the program that we had, because this is pretty clumsy, and in performance terms, it's not going to work very well. We can get a hint about what we want to do by going back to our original program. So,
okay, so we want to improve this program. What can we do? Well, for instance, we see all the values highlighted on the string here. We can get rid of the add method because the add method, only thing it does, it adds 254, so which can be replaced with simply that. So if you can get rid of add method, we have simplified compute. We don't need to call another method, and hence avoid all that overhead that we saw before, setting up the stacks, unwinding the stacks, and all that stuff.
All that overhead? How much overhead is there, actually?
Well, we need to measure, measure and guess.
Right, go ahead.
So how do we do that in 2019?
Well, we use JMH. If you want to actually find out how long it's taking your machine, any instructions in the JVM to execute, you want to use a micro benchmarking harness. You really should. Get current milliseconds is no longer acceptable. So we're going to use JMH every time. JMH is the micro benchmarking harness that's actually built into the JDK. So it's a really obvious choice. If you want to measure performance, get to know JMH. And what does JMH tell us about what happens when we do that manual optimization that the last slide showed? It gives us results like this. We find that we've got an improvement of around about 25% in the performance just by taking out that one method call, by doing the code in line. So that's okay.
Yes.
But it's not that great, because I think nowadays, aren't we meant to be writing very small methods and inlining all of our methods by hand the way we did just then and putting them into one big glutinous mass of code isn't really going to be a great idea. Supposing instead we could get it done automatically for us, but we could keep the source code readable and maintainable, but we could actually get the advantages of inlining automatically done for us at runtime. That would be really cool.
Okay, so what you see here is basically a simplified picture, because we are saying that bytecode will always run in interpreted mode, and it's essentially producing unoptimized code, the templates that get executed. While the reality is a bit more subtle than that, because normally the interpreter will keep the profiler, it will watch and gather the profiling information like method invocation counts, loop back edge counts, and stuff like that. And once a certain threshold will be tripped, it will kick in the JIT compiler and tell it to optimize that particular method because it's going to benefit from the optimization. So in other words, JVM never will optimize the whole code like static compilers do. Like if you compile C++ with -02 or -03, it's going to optimize the whole code. Java doesn't do that. It runs your code interpreted for a long time and then only will optimize pieces that are actually hot code and going to be used frequently. So let's see. No.
So without inlining, the code that we're going to get generated, the native code that is generated for our little program looks like this. This is the key part of what the compute method does. This is the key part. That was the benchmark compute method. This is what the actual compute method that we were looking at does, and this is what the add method does. So
I guess what we're really trying to say here is that the stuff that we did with add method, we inlined the body of the method into the caller. This is called inlining. And this is the mother of all optimizations, paraphrasing Cliff Dick. So once inlining is happening, lots of things can happen as well. Lots of other optimizations will unfold. Because without inlining, as you see here, we are not running in the interpreter anymore, but we forbid JVM to do inlining. So JVM is constrained to look at the one method at a time. It can only do as much optimization as within this method. That's it. So it cannot see past the method boundaries. And if you don't disable inlining and let JVM do the inlining, as you see, all our code disappeared. All compute and add and everything disappeared, and we have constant 255 put into the register and return.
So that's inlining, and it's also constant arithmetic as well.
It's constant folding and some other optimizations all bolted together, all playing together nicely. So at the end, this is what is getting executed. If you look at your Java code and what is getting executed on the machine instructions, quite often totally different things.
And hopefully much better things.
Yes, so what was it all about? Let's look at the results. So we still see our first two results was running interpreter and trying to manually optimize, and then we just run JIT compiler, so we don't run an interpreter. You see the orders of magnitude? So we have like 30x performance difference.
The dash x int flag tells the JVM that it's never to do any compilation at all. So that's missing off the last two lines, and that's why the performance is so greatly improved. If we prevent inlining, then we still find that we don't get the maximum possible improvement that we can get. But if we allow inlining as well, then we see that it drops to something like about 2% of the original cost of the operation. And there are a lot of optimizations that the JIT compilers can do. Hotspot has got some of these. I mean, it's got more than these. These are just some of them. Compiler optimization is a very mature technology, or set of technologies. People have been working out how to optimize compiled code for many decades now, and a lot of that is built into the hotspot compilers. So this is a really important piece of machinery. This is a central piece of machinery to understand if you want to know if you want to understand the performance of your Java programs.
By the way, the reason this optimization exists is the reason why JMH exists. Because if you try to benchmark code manually, for example, like running loops and system current time millis and something, these optimizations will most likely kill your code. And at the end, what you end up measuring is nothing. So cost of calling current time millis 2 times and stuff like that. That's what people see, like, Java is infinitely faster than C++, just because JIT compiler can just erase the code. And it's not. So JMH is built to fight some of those optimizations, so the benchmarking harness code will never disappear, but still allowing your code to be fully optimized under the hood. And since Java 12, we have JMH harness-based benchmarks as part of the JDK. So finally, we have performance tests in JDK. Anyways, let's move on.
All right. So all this is all very well, but at the end of the day, what we end up with here is we've got native code. And if you really want to understand what your Java program's doing, you have to look beyond the native code, because it's not only code that we're interested in. We're interested in the actual performance. So when we actually run the code, well, we actually get something happens. Typically, that's what we get that happens, but we're not always. We hope that we can sometimes get things that aren't stack traces.
Okay, so if there is no null pointer we can actually execute, this thing runs on the OS and hardware, right? Which is quite simple. Like everybody, and we are in the university, there are courses they teach about CPUs. It's something like that, right? It's like central processing unit, talks to memory, input, output, we are done.
Yeah, well, that's certainly how I learned about it N decades ago. I thought computers were really straightforward things. And then, actually, if you then kind of more recently, I looked at what computers are like now, and an example of a picture of a modern processor is something like this. So there's a lot of cache in there, a huge amount, and some of the cache is actually attached to the cores. Those cores have actually got a lot of cache attached to them, and there's a shared cache as well. And what's going on there? What's going on there is that over the years, that processors have become faster and faster and faster, and memory hasn't become a lot faster, and memory buses haven't become a lot faster. They've become faster, right enough. They've actually improved greatly, but the performance improvement of processors is just ridiculous. And so the result of that is that we've ended up with this sort of picture of a modern computer, which looks something like this. So we've got at the top we've got processors, and because getting data and instructions from memory that's at the bottom takes so long. What we have to do is to keep the processors busy, to keep them supplied. We can't just depend on saying, oh, well, I want another item of data, I want another data item from memory. Let's bring it up. Because that takes something like about 300 machine cycles. And so the processor is sitting there wasting time, just drumming its fingers, waiting for data and for instructions to arrive from main memory. So the way around that over the years has been to build up these cache pipelines, which are typically 3 levels, sometimes only 2 levels, and there's something like on this picture, and they're kept fed. So the idea is that the processor will look ahead and it'll figure out what instructions it's going to need some time away, sometime in the future, and it asks for those to be fed up the pipeline in effect. So what you have here is a picture in which the components at the top are fast, they're expensive, they are typically small, so L1 caches are typically very small, but they're fast, they're power hungry, and they're expensive. But they can feed the data and instructions to the cores within just a few machine cycles. And as you go down the levels, they perform roughly 4 times worse at each level that you go down, and they're also a lot cheaper and a lot larger. So this is really important, because the important thing to take away from this is that a cache miss is really expensive. It costs an awful lot of time. A processor will be standing idle if it makes the wrong guess about what data it's going to need, and that data isn't accessible in an L1 cache or L2 cache. If it has to wait for it to come from L3 cache or from memory, it's waiting a long, long time, and that's going to hurt the performance of your program far more than just a few extra instructions. So,
which is very bad news for Java programmers, right?
It's really bad news for Java
because
programmers.
Java is very
reference heavy. Java organizes.
Absolutely.
Java organizes its data in a really, really terrible way. So let's have a look at one of the simple techniques that the processor uses in order to try to work out, in order to try to make sure that it keeps fed with data. It's called stride prefetching. So the idea of stride prefetching is that I've got here a picture of the processor, and under the processor there's these cache lines. They're called the 64 bytes. And the idea of stride prefetching is that the processor watches a pattern of data access and extrapolates it. So here we can imagine that we're going to be reading every second line of data and every second element of data. Just imagine we're stepping down an array, and we're stepping down 2 elements down an array each time. That's the blue arrows. The processor looks at this and says, well, okay, probably this is like a 1,000,000 element array, and I'm going to need to extract every second element from it. So it can prefetch those into cache in time for them to be used. And that's actually really effective. It works really well. Something that doesn't work so well are data-dependent loads. So if you've got data-dependent loads, then which is Java. So if the only way that you can tell what piece of data you're going to want next is by looking at a reference that exists in some object, you have no idea where that reference is pointing to. It's pointing to some object that was created like either many machine cycles ago or just yesterday. And so essentially, your objects are going to start to become distributed all over memory. And stride prefetching simply doesn't work at all. So every data access for a data-dependent load is a cache miss. It's a nightmare. And by the way, if you ever look at the new projects that the Java development, that the Java architecture team are interested in, and you see Project Valhalla and value objects, you see they are really concerned about this, and they're really trying to sort it out. How am I doing for time?
So basically, here Maurice showed one of the process is doing a couple of beds here. One of the beds is a locality bed. The memory you access, you most likely access the adjacent memory, so it's good to prefetch the next memory. There's another bed called temporal bed. If you loaded something, you're most likely going to use it again, so it's good to cache it. So all these things in play allow you to, and the effect of indirect pointers, think about your objects. You call an object, that calls an object, or A.B.C.D. All of these gonna jump into random places in memory, cause cache misses, means slow. Well, with Valhalla, we might get sort of like structs, value objects into Java, where, for instance, if you allocate an array of them, they'll be lumped together. There will not be different objects that belong, contiguous array in memory. But it's not here. It's probably Java 57 yeah. by the new release cadence.
Okay. Right. I'm going to. I'll skip I'll put okay. So let's see how much of a difference cache-friendliness makes. So cache-friendliness is a term that's used to describe whether or not a program really understands the importance of this, or the programmer or the data structure designer understands and is able to handle this one question of hardware optimization.
Can you tell us what you're doing in this benchmark? Just
what I'm doing in this benchmark, I'm simply iterating. I'm simply iterating over a linked list, and I'm iterating over a primitive array. So you might think that since linked list is kind of notorious for its poor performance, you might think I've kind of chosen a data structure that like nobody cares about very much and nobody uses very much. But actually it's going to turn out that array list is not a lot better. And the reason it's not a lot better is because the basic problem for cache friendliness with Java data structures, Java collections, the problem is that they use references. And if you're using references in this random way, there's not a lot that you can do about it. And the difference is really dramatic. Here's the results for iterating over a linked list. There are 4 columns to this table, and they show the performance for 1K elements, 7K elements, 63 elements, and 511 elements. Lists of each of those lengths. And the performance drops off dramatically as you go through the list, as they increase in size. And if we look at why this is, we can see that the clock ticks per instruction are increasing the same, pretty much the same. They're getting worse at the same speed as the performance is getting worse. And what that indicates is that we're not actually performing more instructions. We're normalizing on the number of instructions we're performing. It's not like linked list is doing more work. It's just that the work it's doing is going more slowly as the list gets longer. And if we look at why that is, and again, cycles shows the same kind of thing. See, the number of instructions that are being performed is constant, but what isn't constant is the number of cache misses. Now, you see the number of cache misses, the level 1 cache misses, is going up. Not a huge amount, but it doesn't need to go, thank you. It doesn't need to go up a huge amount, because what I was saying earlier was that even a relatively very small number of cache misses are going to kill the performance of your program. They're much, much more important than you tend to give them credit for. And that's really the real takeaway from this slide. Now, if we look at a primitive array, which of course is very cache friendly, we're iterating over that, and stride prefetching works perfectly. that we see something completely different. And we see that the performance is almost constant, even for a very large array. And the reason for that is that the cache misses, the second line, the level 1 cache misses, is almost zero, even for the large array. So that makes linked list look like a really kind of bad idea. We know it's a bad idea for other reasons. It's very space hungry, which of course is related to this problem. And we know that it's doubly linked, and that's really expensive. And in fact, I feel quite sorry for linked list. Its creator, Josh Bloch, tweeted this recently, and I did feel for it. So like, it's really an unloved child. But I did say that. In fact, ArrayList is not hugely better. It gives, of course, better results than this. But the fact that it's using references and the data-dependent loads mean that the data it's accessing is scattered around memory means that it's also pretty unfriendly to caches. So,
by the way, I have a question. What kind of magic did you use to see the CPI, cache misses, and everything?
Oh, that's a really important question. What kind of magic did I use for that? I used JMH. So JMH is actually this fantastic tool. Thank you very much for reminding me. JMH is this fantastic tool which will actually allow you to hook up the hardware performance counters. Because this is stuff that, these kinds of figures is stuff that you do not normally see, obviously, with a profiler. Because in order to see the number of cache misses there are, you've got to get right down into the hardware. And profilers don't normally do that. So being able to use things like perf and perfasm, tools that are provided typically by Linux and are actually supported by the hardware manufacturers, is absolutely vital. JMH is exactly the tool that you want in order to be able to hook that up. And this is just output from a JMH run with perfasm hooked in and just reformatted.
Right.
Conclusions?
So in conclusion, we looked at the soup of what's happening if you take the Java source code and went all the way to the CPU instructions being retired, executed, and looked at the cache structure of the CPU. There's a lot of stuff. The question is, does it matter? You know, I think it is, and I think if you don't understand what lies underneath, or actually that makes you a better programmer if you know what's going on. The tools, some of the tools that we have shown are proven to several people, or I know personally, and then I used also some of them in the despair, where they were invaluable. You couldn't get into information like, you know, fault sharing problems, stuff like that, where you need to look at CPU counters. No other profiler will show it to you, and that's invaluable to actually solve real problems and you know, save the day. So what's your take on it?
Yeah, I mean, I think there's always a problem with many levels of abstraction, like we have with Java. We're a long way removed from what's actually going on in the machines, and obviously we should be grateful for that. A lot of the time, you don't really want to be writing assembler, x86 assembler anymore. But abstractions always leak. You never really can understand fully what's going on from simply looking at them. And there's always going to be corner cases where it's really important for you where it really counts. You're going to be really ahead if you have a picture of what's going on all the way down. So I think it's important to your development your rounded development as a programmer. Sometimes it's really important for sorting out a performance problem to have a feel for this stuff. And in the end, I mean, like, I think, you know, we should actually be in control of our own work. We should understand what we're doing. We shouldn't be believing in magic. And sometimes if you don't understand enough of what's going on, it looks like magic, but it's not magic. It's just a sufficiently advanced technology, to quote Arthur C. Clarke. So there's a lot to understand here, but it's all available. There's a huge number of resources available on the internet. I mean, you don't even need, buying books is a good idea, but nowadays you hardly need to do that at all. The Mechanical Sympathy blog is Martin Thompson's blog. He's the guy from whom I learned a huge amount about this stuff. And always worth seeing what he writes. JMH is always worth learning about. If you're going to be doing any performance measurement, it's really valuable, or just to understand what's going on. The JIT Watch tool is a fantastic piece of software which actually will tell you, does a lot to tell you about, to monitor the behavior of the JIT compiler, to tell you about what it's outputting. It really improves your understanding of what's going on. And there's some great videos from Chris Newland, who wrote this tool, that explains what's going on. It's great education. And the last link is just what you need in order to get, I think it's JIT Watch to work. Is to get the perf assembly to work. Yeah.
All right.
So, thank you very much for your attention in listening.
Do you have any questions?
No. We finished some time for questions, and we don't have any. Awesome.
What was that? Have a good end of the day.
Yeah.